Everything starts with an idea, a spark, a what-if moment. What if we could build something so small you couldn't see it with your own eyes? It's not about making something tiny just for the sake of it. No, it's about pushing the absolute limits of what we believe is possible. Imagine wanting to create a gift for someone, but not just any gift. You want to give them an entire world. You want to give them a character they love. You want to give them a memory, but have it fit on the tip of a needle. That's the kind of thinking that gets my maker brain buzzing. It's a challenge that combines art with some seriously high-level science. It's the ultimate expression of precision. This initial thought process isn't about the how just yet. We're not worried about printers, we're not worried about lasers, we're not worried about microscopes. Instead, we're in the realm of pure imagination. What story do we want to tell? Maybe it's a tiny astronaut waving from the surface of a grain of sand. Or perhaps it's a miniature dragon with scales so fine they can only be appreciated under immense magnification. The idea has to be compelling enough to justify the incredible effort that will follow. It's this passion for the concept, this narrative, that fuels the entire project. Once we have our idea locked in, our ballerina, we move to the digital workshop. This is where the figurine is born, not in the physical world, but as a collection of data on a computer. We use powerful three-dimensional modeling software, used to create visual effects for blockbuster movies, to design complex video game characters. At this stage, the figurine on my screen is a giant. It's massive, filling the entire monitor, allowing me to zoom in and sculpt every single detail with incredible precision. I'm not thinking about its final minuscule size just yet. I'm focused on making it perfect. I treat it like a real sculpture. I use a digital stylus and a tablet, which feel a lot like traditional sculpting tools. I can push, I can pull, I can smooth, I can carve the digital clay. For our ballerina, I spend hours on the flow of her dress, making sure the digital fabric has realistic folds. I define the muscles in her legs. I define the delicate structure of her hands. I define the expression on her face. This is where the artistry really shines. Every click, every stroke of the stylus is adding a piece of the story. It feels like I'm building a monument, even though I know its destiny is to be smaller than a whisper. Now we have our beautiful, huge, digital ballerina. The next step is to prepare this file for a very special kind of printer. It's not as simple as just hitting print. We need to convert our artistic model into a set of precise instructions that a nanoscale three-dimensional printer can understand. This process is called slicing. The software takes our three-dimensional model and slices it into hundreds, sometimes thousands of incredibly thin, horizontal layers. Each slice is like a single page in a massive book that describes the ballerina from the bottom of her toe to the top of her head. Think of it like a CAT scan, but for our digital sculpture. Each slice is a two-dimensional cross-section. If you were to print out every single one of these slices on paper and stack them up, you would have a rough approximation of the ballerina's shape. But at the nanoscale, these slices are unimaginably thin. We're talking about layers measured in nanometers. We're not using a regular three-dimensional printer that you might have in your workshop at home, the kind that melts plastic filament. Oh no. To build at the nanoscale, we need a machine that sounds like it came straight out of science fiction, a two-photon lithography system. This is less like a printer and more like a high-tech science experiment. The machine is often housed in a special clean room to prevent even a single speck of dust. It sits on a massive granite block to damp vibrations. The ink is a special, light-sensitive liquid polymer. We place a tiny drop of this clear, gooey resin onto a glass slide, our build platform. This drop of resin is where our ballerina will be born. The entire process happens inside that droplet. The key is an ultra-fast, intensely focused laser. The clever part, why it's called two-photon lithography. The laser alone isn't powerful enough to solidify the resin. It only works when two photons hit the exact same point at the exact same time. This two-photon effect gives us insane precision. Solidification only happens at the laser's focal point, a spot smaller than a micron. That means we can draw in 3 dimensions inside the liquid resin. The machine's computer reads our sliced G-code and directs the laser with mirrors, and lenses. It zaps one point, creating a single hardened voxel, a 3D pixel, then instantly moves to the next point. After many hours, the printer finally finishes its job. The laser shuts off, the silent work is done, but if you looked at the glass slide, you'd see nothing. Just a clear drop of gooey resin. Our ballerina is still in there, hidden, trapped in liquid. Next step, the grand reveal. It feels a bit like developing old-school film, a moment of truth. Did the print work? A carefully controlled chemical bath is next. We pick up the glass slide with the droplet, gently submerge it in a solvent, usually isopropanol. The solvent's job, wash away uncured resin. It won't touch the solidified ballerina or supports. As we agitate, the uncured polymer dissolves into the solvent. It's delicate. The structure is unimaginably fragile. You must be incredibly careful. This is the most nerve-wracking part. Did the supports hold? Did any fine details break off? Was there a microscopic vibration that shifted a layer? We're washing away the scaffolding, blind. You can't see the figurine, so you trust timing and chemistry. After a few minutes, we remove the slide and do a final rinse. The slide is clean. It still looks empty to the naked eye. No visible sign of hours of work. Is she there? Did it work? Only one way to know. Move to a powerful microscope. The ballerina exists on the glass slide. She's completely invisible to the eye. Smaller than a speck of dust. Clearer than glass. Now we must see her for the first time to prove the journey worked. This is the moment of judgment. To see our creation, we can't just use any old magnifying glass. We need a machine that can see things at the scale we've been working at. We bring our glass slide over to a scanning electron microscope, the SEM. This is a beast of a machine. It doesn't use light to see. Instead, it shoots a beam of electrons at the object. Those electrons bounce off the surface. The SEM reads that signal and builds an incredibly detailed, high-magnification image. We carefully place the slide inside the SEM's vacuum chamber. We pump all the air out so the electron beam can work. Then we turn on the beam and slowly bring the image into focus on the monitor. At first the screen looks like a vast empty plain, the glass slide. We navigate across that landscape hunting for our ballerina. Suddenly a shape begins to appear. A tiny, intricate form emerges from the gray background. There she is, our ballerina, perfectly poised. The feeling is pure elation. So just how small is our ballerina? It's hard to wrap your head around the numbers, so let's use some comparisons. The entire figurine from the base to the top of her head might stand about 100 microns tall. A micron or micrometer is 1/1000th of a millimeter. The average human hair, as we said, is about 80 microns thick, about 100 microns thick. This means our entire perfectly detailed ballerina could literally stand on the cut edge of a single strand of your hair. She is so small that a single grain of table salt would look like a colossal mountain next to her. To truly appreciate this scale, imagine placing her on the head of a pin. The head of a pin is about 2 millimeters across. You could host an entire ballet recital on there. So, what do you do with a sculpture that you can't see? It seems like a valid question. The answer is, more than you might think. For one, they make for the most unique gifts imaginable. Imagine giving someone a small display case with a powerful magnifying lens built in. Inside, mounted on a pedestal, is a nano figurine of their favorite superhero, a tiny sculpture of their beloved pet, or even a miniature version of themselves. It's a conversation piece like no other. It's not just a gift, it's a piece of the future you can own. But the applications go far beyond novelty and art. These same techniques are being used to build incredible things in medicine. Microscopic cages, programmable nanobots, delivering medicine directly to cancer cells while leaving healthy cells untouched, tiny complex scaffolds that help regrow human tissue. Our ballerina is a fun demonstration, but the underlying tech could revolutionize drug delivery. And don't forget, exploration and education. These figurines get people excited about science. Show a student a sculpture standing on a human hair and watch their imagination. Physics, chemistry, engineering, art. It makes nanotechnology tangible and exciting.